Okay, just a reminder again of our main result of this chapter, which is if an object is in uniform circular motion on a circle of radius r with speed v, the acceleration at every point in time of the object points toward the center of the circle and has magnitude v squared over r. Let's apply this to a more complicated problem. This is something called a conical pendulum. A normal pendulum would just sort of swing back and forth, but this pendulum is, there's a string attached maybe here to a ceiling, and it connects to a mast down here. The string is supposed to be like a light string. And then instead of having it swing back and forth, we push it so it goes in a perfect circle. It doesn't look like a circle here, but that's because we're looking at it somewhat edge on, but we're supposed to imagine this thing is moving in a horizontal plane in a perfect circular path along the direction shown there. And the question we want to answer is, given some specific details about the setup, the mass has mass 2 kilograms, the length of the string is ½ meter, and the angle between the string and the vertical line going through the center of the circle is 35 degrees. Sometimes people will say that string is at 35 degrees to the vertical. Given that, what is the magnitude of the acceleration in this example? And as always, if we want to find an acceleration, hopefully we know something about the forces and we can use F net equals ma, both x components and or y components, and we have to decide what x and y mean. So let's get into it. Newton's second law for x component says the sum of the force x components equals max. In order to use it, we have to have a free body diagram, and we have to assign some axes to it. So the object we're going to use for our free body diagram, I'm just going to imagine I'm drawing that object at the instant it's shown right here, where it's sort of as far left from my point of view as it can get. So there's the object. What forces are acting on it? Well, there's a weight force, of course. This is a 2 kilogram mass, so its weight is 2 times 9.8, directed down. What other forces are on it? There got to be some other ones, otherwise it would be in free fall, right? The only other force that we can see is the tension in the string. I don't know what that tension is, but the tension in the string is always directed along the direction that the string is pulling, right? Strings can't push on things in different directions. They can only pull in the direction that the string is oriented. So in this case, the tension is directed at an angle of 35 degrees away from the vertical. You can kind of see that because this vertical line here, this vertical line here are parallel, and this angle and this angle are alternate interior angles, and therefore they're equal, if you remember that factoid from geometry. So that's our free body diagram. I don't see any other forces that we should include. And now the question is axes. How do we decide whether we should? It seems like the two logical choices is either align one of our axes with the string or do horizontal and vertical. Ask yourself, which do you think we should choose in this case in order to simplify the problem as much as possible? And the rule of thumb that we've always used before and we'll always stick to is if you know the direction of the acceleration, choose one of the axes to point along that direction. We do know the direction of the acceleration. At this instant, it points directly to the right, towards the center of the circle. So I'm going to make that directly to the right direction x, and we'll call the perpendicular vertical direction y. We definitely are going to make things more complicated if we use tilted axes in this case. All right, so using sum of the force x components equals max, let's see. This weight force in my axes has a 0 x component, right? To go from the tail to the tip, I don't have to move along x at all. I only move along minus y. So that has a 0 force x component. So this is the only one I need to include that's not 0. Its x component is first of all going to be positive because it's pointing more or less over into the positive x direction. And the magnitude of that force x component is going to be the length of this side, right? That's parallel to the x-axis. So drawing in that right triangle, starting with the hypotenuse, what do I do to get to this side? I go across the angle that we know, and therefore I multiply t times the sine of 35 degrees. So that's why our only force x component is t times the sine of 35 degrees. Okay, that's equal to the mass of the object in the free body diagram, that's 2 kilograms here, times the acceleration x component, and the acceleration is all along x, and we already know the length of the acceleration. It's v squared over r, right? Well, the only problem is we don't know what v is. We know we might be able to figure out what r is, but we don't know what v is. So it looks like I could solve for the acceleration, except that if I only knew t, if I knew the tension in the string, I could find that acceleration. And so our goal now is going to be to find the tension. Since we don't know the speed, it seems like more straightforward to find the tension, because to find the tension, what I'm going to do is sum of the force y components equals may. I know something about that because I haven't really used this weight force yet. The tension's clearly going to change as the object is more massive or less massive. Okay, both these forces have non-zero y components. The tension y component is going to be the length of this vertical side of the right triangle. That's t times the cosine of 35. That comes in with a plus sign because it's pointing more or less in the plus y direction. And this weight force comes in with a minus sign because it is definitely going along the minus y direction. From tail to tip, you go along minus y. And that's equal to may, but ay is 0. We know the acceleration points in this direction, and therefore the component of the acceleration along this vertical direction is 0. Or another way to think of it is, look, it's staying in the same horizontal plane. If it were accelerating upward or downward at all, it wouldn't be staying in the same horizontal plane. It starts out at rest in the horizontal plane. It would have to start moving upward, so it can't have any non-zero acceleration component. So ay is 0, so the right-hand side is 0, and that allows me to solve for t. T is 23.93 newtons, not worrying too much about the significant digits there. And now that I've got that, I can plug into this relationship up there and solve for a, right? Plugging it into my calculator, I get a equals 6.86 meters per second squared. So that answers the first question, and second question is, what is v? If I would have known v to begin with, I might have been able to just plug directly into v squared over r to get the magnitude of the acceleration, but it wasn't clear that I knew v, and I also didn't really know r either directly. Although here, if I want to know v, I already know the magnitude of the acceleration, and the magnitude of the acceleration is v squared over r, so maybe I can solve for v that way. Of course, the first thing I've got to do is figure out what r is. And I can figure out what r is from this diagram here, right? We love right triangles in physics. There's a right triangle I can look at like this. This side of the right triangle right here is r, right? That's the radius. Remember, this r is not 0.5 meters. 0.5 meters is not the radius of the circle that this thing is traveling on. When you're in uniform circular motion, the r always means the radius of the circle that you are traveling on as your path, okay? So, if I know the hypotenuse is 0.5 meters, what do I do to get to this side over here, which is r? I multiply by the sine of 35 degrees because I'm going across the angle. And that's very strange because I have the cosine of 35 degrees written down here. So that must be, I'm not sure if there's a calculational error in this particular problem or if I just mistyped it when I was doing it there, but it looks like it should be r is 0.5 times the sine of 35 degrees, and I'm going to set that equal to the known magnitude of the acceleration. We already figured out the acceleration was 6.86. I'll have to go back and check in my calculator whether I just have a typo here in the slides or I actually miscalculated something. Who knows? Let's hope that this number is right and I just mistyped a sine as a cosine there. All right. So in this case, we wouldn't want, if I asked you, oh, what's the centripetal force here? Well, a centripetal force is not a force at all. In fact, we don't want to use that phrase or those words at all because it suggests that there is a single force that causes this centripetal acceleration. And there's not in this case. There are two forces. The tension of the string, and it's not pointing along the direction towards the center of the circle, and the weight force. It's only the combination of those two. If we add those two vectors, they should add to exactly a force that points toward the center of the circle at that particular time. And so we don't want to refer to a centripetal force. Sometimes when people say that, they think, oh, I've got these two forces, plus there should be a third centripetal force that is causing the circular motion. No. Centripetal force isn't a force at all. It's just another name for the sum of all the forces. So let's forget about using that phrase centripetal force and just talk about, hey, we know something about all of the forces that are acting in this case. There happen to be two of them. Okay, let's go on to a worksheet, another example of uniform circular motion in which there's more than one force that's causing an object to move in uniform circular motion. And that object here is going to be you, or whoever's riding this Ferris wheel around. So we've got a rider who is first at position A, then later at position B as they're going upwards, and then passing the top position C, all while moving at a constant speed. So this Ferris wheel, we're told, has a radius of 15 meters and rotates at a rate of 7 RPM. And I say, note here, that's actually, for this size Ferris wheel, a very fast rotation rate, and you would feel probably a little bit scared as you rounded the top of this Ferris wheel. It would be a frighteningly fast ride, but I thought, just to make it a little bit more dramatic, I'd speed up make the speed a little bit faster, even though 7 RPM doesn't sound very fast. For this size Ferris wheel, it actually is. And we've got a 75 kilogram rider who moves in the direction that we would call counterclockwise. Counterclockwise, sometimes I abbreviate that as CCW. That's opposite to the direction the hands of a clock spin. This is going the opposite direction. It's the direction mathematicians like to go around circles, the way I'm having the move here. So the rider we're imagining is sitting on a perfectly flat seat, and the fact that this cage, we're going to imagine the cage always stays vertical, so the rider's seat is completely flat. The rider's feet don't touch the ground, so their full weight is on the seat, and on top of the seat, underneath the rider, is a scale that reads in newtons, so we can sort of gauge how heavy they feel at any particular time. The reading on the scale is sometimes referred to as the apparent weight of the rider. In other words, the rider might feel heavier or lighter at certain points in the ride. That doesn't mean their real weight is changing. And the first question I'm asking here is, what is the rider's real weight, not apparent weight? The real weight, of course, I'm going to answer the first two questions together just to send you on your way. And then I'm going to have you try to do the questions that ask about position A, B, and C. Just remember, toward the center of the circle, v squared over r. What's the rider's real weight? Well, as long as you're near the surface of the Earth, it doesn't matter how you're moving, your weight is mg. And if you're asked for the direction, it's downward towards the center of the Earth. So 75 kilograms times 9.8 meters per second squared is 735 newtons. So that's the rider's real weight in newtons. What's the rider's speed relative to the ground? Well, we get to practice here with that distance over time trick. We know, remember, in this case, I changed my mind after I wrote my solution out, 7 RPMs. I guess 10 was a little bit too thrilling. So 7 RPMs is what you should see in the worksheet that I've actually posted on the website. And that means that we can calculate the speed by how far they moved divided by the corresponding time, and we can choose any time that's convenient or any distance that's convenient as long as we use the corresponding one in the numerator or denominator. And for us, when you're given the RPM value, that revolutions per minute means we know something about what happens in 1 minute, and I've changed that to SI units of 60 seconds. So in that time of 60 seconds, what happens? The rider goes through 7 2 pi r's, 7 circumferences, right? So 7 times 2 pi times 15 meters. And that gives us a speed of 11.0 meters per second. All right, now we're going to go successively from position A, then we'll do position C, and because B is a little bit more complicated, we'll do that one last. Draw a free body diagram for the rider at position A. Show all of the forces on the rider, and then use that to answer what will the scale read when they're at A. One of the forces on the rider should be the force of the scale on the rider. All right, we'll be back with the solution.